Welcome to this deep dive into satellite image classification using deep learning. In this video, we'll walk step by step through building, training, and evaluating powerful models for land cover classification. From setting up a clean development environment to exploring our dataset visually, every stage will help us understand how AI learns to interpret complex satellite imagery. We'll start with a custom-built convolutional neural network as our baseline, then enhance performance with transfer learning using MobileNet v2. Along the way, we'll analyze training curves, confusion matrices, per-class accuracy, and prediction grids to gain real insights into model behavior. Finally, we'll open the black box with Grad CAM visualizations, showing exactly what our model focuses on when making predictions. Whether you're an AI enthusiast, a researcher, or just curious about how machine learning can make sense of Earth from above, this video will give you a clear, visual, and practical understanding of the process. We begin by setting up our environment, ensuring every library and dependency is correctly installed. This step may look simple, but it is foundational. Here, we install compatible versions of scikit-learn, TensorFlow, and supporting packages like Pandas, Matplotlib, and Gradio. We also check for GPU availability and enable mixed precision to optimize training speed on modern hardware. Getting this right means the rest of the project runs smoothly, avoiding version conflicts or performance bottlenecks. This is where every great model starts, with a clean, robust environment tailored for deep learning. In these steps, we configure the project parameters and import essential libraries. TensorFlow drives our deep learning workflows, while TensorFlow datasets provides pre-built data pipelines. Scikit-learn helps with evaluation metrics like classification reports and confusion matrices. We also set hyperparameters, image size, batch size, and epoch counts. These are not random values, they're carefully chosen to balance training speed and model accuracy. By fixing random seeds, we ensure reproducibility, making our experiments reliable and repeatable. Every line here sets the stage for building a consistent, powerful model. Next, we load our dataset using TensorFlow datasets. This project uses the EuroSAT dataset, which contains satellite images across multiple land cover classes like forests, residential areas, and water bodies. We split the data into training, validation, and test sets, ensuring each subset represents the real-world diversity of these classes. Preprocessing follows, resizing images to a uniform size and normalizing pixel values for better neural network performance. These steps are critical because well-prepared data is the lifeblood of deep learning. Without it, even the best models will fail to generalize. To make our model robust, we apply data augmentation. Here, images are randomly flipped, brightened, and contrast adjusted. This simulates different real-world conditions, like changing sunlight or orientation, helping the model learn features that remain consistent despite visual variations. In satellite image classification, this is especially important. The same location can look dramatically different across seasons or times of day. Augmentation ensures our model isn't fooled by these changes, leading to stronger, more generalizable predictions in the real world. Once preprocessing and augmentation are defined, we build efficient TensorFlow pipelines for our training, validation, and test sets. These pipelines cache data for faster access, shuffle it for randomness, and batch it for optimal GPU utilization. Prefetching ensures that while the model trains on one batch, the next batch is prepared in the background, maximizing computational efficiency. These optimizations are invisible to the naked eye but drastically speed up training and make our workflow scalable for larger datasets. Before training, we visualize samples from our dataset. These images aren't just for display, they give us a critical understanding of what the model will see. Forests with dense green canopies, blue sea lakes, urban grids, and agricultural plots all present unique patterns. This visual inspection also helps spot anomalies or mislabeled samples, which could otherwise hurt model performance. In deep learning, knowing your data is as important as building your model, and this simple step makes sure we're on the right track from the start. Here we design our first model, a convolutional neural network built from scratch. It includes multiple convolutional layers for feature extraction, batch normalization for stability, pooling layers for dimensionality reduction, and a dense softmax layer for classification. This baseline architecture teaches us how well a custom model can learn from scratch, without any external knowledge. It's our benchmark, showing the raw power of CNNs in processing satellite imagery, even without pre-training. We now train our baseline CNN over 8 epochs. The graph shows training accuracy climbing steadily toward 88%, but validation accuracy fluctuates. This gap signals overfitting. The model memorizes training data but struggles to generalize. To counter this, we use callbacks like early stopping and reduce LR on plateau, which prevent overtraining and adjust the learning rate dynamically. This training phase gives us valuable insights into where a scratch-built model shines and where it needs improvement. Next, we implement transfer learning with MobileNet v2. Unlike our scratch-built CNN, this model starts with pre-trained weights from ImageNet, which already understands generic visual features like edges and textures. This jumpstart leads to more stable validation accuracy around 77% with less overfitting. Comparing both approaches, we see why transfer learning dominates in image classification. It combines pre-existing knowledge with task-specific fine-tuning, delivering faster and more reliable results. Now we evaluate. The confusion matrix reveals which classes are well predicted and which are often confused, like highways misclassified as rivers. The classification report provides precision, recall, and F1 scores, showing residential and sea lake classes performing above 0.9, while others like highways lag behind. The per-class accuracy chart makes these patterns clear, guiding us toward where more data or tuning is needed. This comprehensive evaluation transforms our model from a black box into a measurable, improvable system. Here, we visualize random predictions alongside their true labels. Correct classifications reinforce our model's strengths, while mismatches expose its blind spots. For instance, distinguishing herbaceous vegetation from crops proves challenging. These visual audits are essential. They let us validate performance beyond raw metrics and gain intuition about how our model interprets the data. This step bridges the gap between numbers and practical application. Finally, we use Grad CAM to peek inside the model's decision-making. The heat map shows areas the network focused on while making predictions, overlaid on the original image for context. For example, in classifying a residential zone, the model pays attention to grid-like urban structures. This transparency is crucial. It builds trust by proving that our AI makes decisions based on meaningful features, not random noise. Grad CAM turns our deep learning model from a black box into an interpretable, accountable tool. And that wraps up our journey through building and understanding satellite image classification models. We started from scratch with a CNN, leveled up with transfer learning, and interpreted our results using advanced tools like Grad CAM. This project doesn't just showcase deep learning in action, it highlights how these models can support real-world applications like urban planning, agriculture monitoring, and environmental protection. If you found this video insightful, don't forget to like, share, and subscribe for more content on AI, machine learning, and computer vision. Have questions or want me to explore another dataset? Drop them in the comments. I'd love to hear from you.